start a recording and then share the other screen. Okay. Okay, at the same time, we can talk about the homework through 3-2. That's my whole plan. While we're going through this one, we can just cover the homework 3 in that way. During these 3 days, today, Monday, sorry, Wednesday and Thursday, pretty much we can cover everything that we really need to cover. So within this week, we have to cover, I think, chapter 7, 8, and 9. Chapter 7 is about that indicator variable. I mean, like in chapter 7, pretty much what we are planning to do. Chapter 6, as I said earlier, that it's about the graphical representation. Not that 6. This one. This is in the assumptions of the regression model. You can remember the assumptions of our model, which is called the line, L-I-N-E. L stand for linearity, I stand for the independence, excuse me, N stand for the normality assumptions, and then E for the equal variances. Those things can be checked. Okay. And in chapter 7, we are talking about that, including like a, so far we did for the regressive variable for x-axis, we had the quantitative variable. We can now include some kind of a categorical variable and see how it's going to work. So that's the plan. And then run the regression. Actually, the regression with the some kind of a regressive variable with the qualitative data called the analysis of variance. Actually, it's coming under the ANOVA. We can abbreviate the analysis of variance as ANOVA. That in that one, or you can say the group regression. We can talk about that one. And in addition to that one, chapter 8 is the key part, that the selection procedures. We can talk about the selection procedures in chapter 8 during this week. Okay. Selection means like how to select the best model at the end of the day. Okay. How to select the best model. It's in chapter 8. Chapter 8, I think. Yeah, chapter 8. See? Variable selection, which variable to be selected. There are 3 types of selection. There are so many procedures for us to select the variables at the end of the day. Mainly, we can talk about that variable forward selection, backward selection, stepwise selection, those kind of things. In chapter 9, we're going to get back to the, as I mentioned, the analysis of variance again, which we pretty much going to cover in chapter 7. I mean, like, that's a kind of a same thing. Same thing. In chapter 7, we have a indicator variable, not this one, sorry. 7. This one. They both would have pretty much the same setup. See? Using indicator variable, or those are called the dummy variable. We're gonna just utilize a certain kind of a dummy variable, temporary variable, to just do that, get our model run, or that get our results. It's this one and this one pretty much have the same setup. Okay. And the following week, I think we have only 1 chapter to be covered, 1 or 2. Okay, it's not a big deal. Okay, so we can slowly and steadily build up what we really need. And while we going through these ones, we can go through our homework as well. So let's say that little bit, have a look at it, chapter 6. Okay, we can just go through this one real quick and see what we are supposed to look at. This is in the assumptions of the regression model. You can remember that this is multiple regression model. We have a k many regressive variables. See, k many. In most cases, that we had like a 5, 6 regressive variables. See? And we have a number of parameters to be estimated. How many? 1 more than the regressive variable. We know that one. And this is the part that we always looking into, because without this part up to here, this is called your estimate. That's the one that you can, that part you call the deterministic. Once you add this error part, the whole thing become randomized. That's why you have to pay very serious attention for the error term. And then we saw that it has these top properties. We expect the average disturbance to be 0. So the regression line passes through the average value of what? See, They expect the average disturbance. That means they say definitely, if you go ahead and get any data set, even in the sample version or population version, if you go ahead and calculate the errors, I'm not talking about the error square, just simply errors for each and every data points. That means the error is the, you know how to calculate the error in regression, that y minus y hat, okay, y minus y hat. So y minus y hat means that the equation of the regression line that would give you the error term. If you get these error terms and draw a histogram for error terms, that histogram would have the center at zero. Zero would be the center. That's why they say the average disturbance to be zero. So the regression line pass through the average value of y. Okay? So the regression line can pass through the average value of y, okay, which is zero. The disturbance have the constant variances. They all have the constant variance. The disturbances are normally distributed. The disturbances are independent. So we saw this one very crystal clearly that at a certain point, I can cite something that I did for one of the students over here. See here. So see this. This is some kind of example with the categorical variable, but just say that for our convenience, I'm going to say these are category. It doesn't matter, categorical or qualitative, doesn't matter. These are based on something I did. It's easy for me to show this one with the aid of this one. I'm mainly focused on this one. They have the non-smokers, former smokers, and current smokers, how they're going to affect to that some kind of a certain diet. Based on that one, I have population version and the sample version. And here, let's say for a given this one, you know, for a given this one, for a given X, we have a certain number of values, not too many values. But in population version, we have infinitely many values. They were easily can put it into a histogram, and then you can get a smooth curve scheme in the top of that one. And then if you get the error terms and then draw something like that, the error will have the zero. That's why they say error will have zero. And the regression line can, that's why they say the regression line can easily see passes through the average value of y. See, so that the regression line can pass through the average value. See, the regression line can go through this one. See, average value of these y values because that the error has a zero variance. Sorry, zero average. See, that's what they say. So that the regression line passes through the average value of y. So that means that that's the same thing. I'm gonna get it. This one over here we played of. So see, if you get the x value over here, say x-axis. This you have a response on this one. Y means a response. Response variable. A particular response variable. This one x, your regressor variable, regressor or explanatory or whatever name that you can call that one. Variable. See, for a given any x value, let's say that x1 or any x value, okay, they have infinitely many values. You do this one for all the x values, and you can go like that. They say you can have this one. I'm going to say this one as average. See, these are the averages. Center. The regression line can easily go through this one that this average is, we're going to say mu of y or expected value of y, or you can say expected value y of given x. Either way, it doesn't matter. That's the same thing. They can go through that one. Why? Because you have an error term, I'm talking about the error rather than y. Error has a center zero if it is zero. And have a bell-shaped distribution. See, bell-shaped. How do you make the error? Y minus y hat. This is y hat. You know that in this case, this is EY. Okay, EY. Okay.
So you can say instead of this one, y minus ey. It's the same thing. Y hat, I'm going to use example version, but that's pretty much the same thing. Get rid of this one. Clear. Error is nothing but y minus expected value of y. This is my y. This is my y. This is my expected value. This gap is error. Error they denote by something called epsilon. This is error. That's why error has the properties. Error has a error is distributed like bell-shaped distribution. And if you go ahead and look at this spread for all this distribution for error that we can, they have the same variance. Variance the same. Variance would be sigma squared. So called the sigma squared. That's the same. That's the same from close place to place, and it's bell shape. It's bell shape. The distances are normally distributed. They are independent. That's very true. I mean, like they are independent from each other. This one, y and error, would have the same type of distribution, bell shape. Only difference, error has a mean value ey or mu y. Error has a mean value 0. Error is always 0. So see, most of the error been clustered around 0. See, that's why they've been equally distributed among along this about this line. That's why that when you're going to add all the errors, error would add to 0. That's why you cannot do that's why we're going to square that one. Sum of squared error, can you remember? SSC, we get that one in ANOVA table. Those things we discuss up to a certain extent. Okay. So those are some assumption. Assumption can be checked. See? So when it's come to the sample version, it's going to be y minus y hat, that error. This is in population version. It's in similar fashion, you can talk about this error. See? Error in sample version as well. See? So how could you going to check those? You really need to do something. You get the residual plot versus the x value and see how they behave. See? Residual versus x. See? Mean of 0, no pattern with x. See? Okay, look at here. The other one is the residual versus standardized. You can standardize as well. What do you mean by standardize? You go to the residual, get the residual, you're going to order from the lowest to the highest one and get its mean value, and get the standard deviation of the error. And then you can easily standardize. How do you standardize error? You can error standardize too. See? Error. See? Let's say we go to this one, I'm going to say population version. Population version. If you go to sample version, pretty much this one x, this one y, it's been scattered all over the places. See? You don't have those kind of graphs. You have y hat here. It's nothing but b0 plus b1x. It is only one. And this is y. And y minus y hat is nothing but error. That's the error. Or in this case, we're going to call the residual. Residual denoted by e, y minus y hat. And if you draw the histogram for error, and then got the smooth curve scheme in that one, its mean would be 0. And the standard deviation would be sigma, or variance would be sigma squared. They would be the same for every error. Every error. Okay, that's the same. The same. So if you're gonna get these values, and then how do you standardize? See, how do you standardize error? You see, error standardize. You go to error term, minus the mean of error divided by standard deviation of error. That's how you're going to standardize error. Error has been standardized. Error has been standardized. That means error bar is E bar. See? E bar is 0. See? 0. Simply you can get the only standard deviation you can find for any data, even for the error. See? Residual versus this one. See? That's a 0. See? Look at the 0. It should be, pattern should be that scattered equally on about this line. Then these are the plots that you have to check into that those properties. Residual versus normal quantiles. You can check the normality. Residual versus predicted value. That means y hat. Okay. Residual versus predicted value. That means x. Check the, excuse me, linearity and constant variance. This one constant variance on. Residual versus the order observation will check the independence. In addition to that one, even though that by looking at the graphically, you can make a conclusion about whether these error terms are satisfied that the given assumptions, line, L-I-N-E, line, linearity, see, check the normality, check the linearity, L, I, independence, I, N, normality, see? Normality, and E, constant variance. See? L, linearity, I, independence, N, normality. The last one is constant, equal variance. Constant variance means equal variance. But these graphical representations are sometimes not enough for you to verify that whether the assumptions are already satisfied. Then you're going to go ahead and look for some kind of a mathematical or statistical test. See, for the check the constancy of the variance, you can check with the Brown force modified Levin test, Wishphagen normality test can be just checked with the Kolmogorov-Smirnov. Independence of error can be checked with the Durbin-Watson test. So we're not going to go detail to this. I'm just barely mentioned that how they're going to differ. This one differ from what I'm talking about. These are like a graphically you can figure out. Just like when the data test set has been given, you don't know whether how they're going to behave. First thing you're going to do, first and foremost thing, you're going to draw some kind of a graph. The major graph would be the histogram. The histogram will tell you the shape, center, skewness, kurtosis, and spread. Those all can be easily verified by looking at about the data set. In a pretty much similar fashion, if you want to check that the residual is going to satisfy the given assumptions, these are the graphical representation. Graphically, you can check, or mathematically, you can check using these tests. Okay. And these are the diagnostic tests. These tests are normally using for even for the, rather than for the goodness of fit, you can use for the lack of fit. You're gonna look, go to the best scenario rather than go to the best scenario. You go to the worst scenario and see, oh, what is missing over here for me to make that my model the best? See, lack of fit. Its counterpart called the goodness of fit. How well that my data being fitted into that given model, or that if there's any failure, or if that model not gonna very well explain that the given data, then you're gonna move on to a different kind of model. You can remember in the very beginning we were trying the linear model. Later on we move on to the non-linear models. There are 3 types of non-linear models we discuss in this class. One is called that polynomial regression model, and the second one inverse regression model. The third one called the inverse model. Sorry, the log model. So we did a broader discussion on that one and check how they're going to work. And in some scenarios that we were thinking about, that adding that more variables to that. But some variables not going to even explain very well that the y variable that we have for our discussions. You see, plot versus the test. If you are uncertain of
What to conclude after examining the plots? You may additionally wish to perform hypothesis test for model assumption. That means normality, homogeneity of variance, and independence. Those things. Assumption is for the normality. That's line. Line. See, line, linearity, normality, homogeneity means like this one. The equal variances and independence. These tests are not replacement for the plots, no, but rather supplement to them. Note of caution, plots are more likely to suggest remedy and significant test results are very dependent on sample size. More likely to suggest a remedy and significant test results are very dependent on sample size. So you got to be very careful when you're going to run some kind of a test. Sometimes again, you have to have the ample that size of that the sample for you to run that particular test. Okay. There are another remedial measures that we can talk about. Transform X if relationship non-linear. Trans of Y if violation of constant variance and of normality assumptions. Use the box Cox to come up with the best transformation on Y. Okay. So there are so many ways to we can get this done. See? So you use the transformation. We saw the transformation. We took the natural log on X as well as on Y. Or X only, Y only. And then we just fit our that different kind of models to data. The sub-box transformation. See? So there are so many ways we can check that those kind of things. So this is the normality probability part. We were mentioning about in order to check at this point what is the normal see normal probability part. How could you gonna get that one? That is nothing but arrange your X values in ascending order. Arrange. To calculate this value for each and every data point, where I is the position of the data value in the ordered list, and N is the number of observations. So you're going to get the I value, let's say that this is the order. The fifth order, 5 minus 0.375 plus divided by N means let's say 10 data points, N plus 0.25. These are some kind of a that perturbation. Perturbation has been added to and subtracted from this one to make this formula very strong and concrete. And then find the C-score for each F5. For this one, you can easily find the C-score, corresponding C-score. Then plot your X value on the horizontal axis and the corresponding that Z-score on the vertical axis. That's what we call this something like this. From this graph, you can, normality plot. That's how you're going to have those normality probability plot would be the C-score versus X value. X value is going to be there for sure, but you're going to arrange that one. They're going to do both. X value will be rearranged, and that rearranged one, you're going to find the Z-score that would be plotted against its own value. Okay. And how to check the linearity? Although sometimes we can see evidence of non-linearity in an XY scatter plot. Scatter plot would tell you the non-linearity. In other cases, we can only see it in a plot of the residual versus X. Residual versus X. If the plot of the residual versus X and versus an X shows any kind of a pattern, it both shows a violation and a way to improve the model. Let's see, look at this one. See, look at this one. Weight has been weight versus not the residual, weight versus these are scatter plots. Height, sorry, height. See, weight and height. You saw that scatter plot. See, all assumptions are satisfied if they're going to fall into this kind of a ribbon. See, all data points were like a very equally scattered below, above and below the regression line. See, above and below the regression line. Look at. If you see something like that, just go ahead and say all assumptions are satisfied. But sometimes some will see off to this side, see, some are off to this side, then non-linear term in model. There's a non-linear term in the model if you saw this kind of a pattern, like this. Heteroscedastic, there's a noise. That means the variances are not the same if you see this kind of pattern. See, some of them are off here. Some are very, see, condensed over here, see. But all of a sudden they were that spread away, see. So this pattern would tell you the heteroscedastic noise. On the other hand, it's corresponding the residual versus height plot, residual versus x value. See, as I mentioned, residual versus, see, residual versus x. Catapult you can utilize too. X versus y versus x, or residual versus x. See, y versus x, or its counterpart residual. How do you get the residual? Y minus y hat. Y minus y hat. Those values for each and every data point, you can calculate the residuals. We're not going to square that one. We keep that one. Plus or minus doesn't matter. We keep those. And then you're going to get the residual on the y-axis. Again, x on this one. If you see this kind of a pattern, very nicely spread out. See, along this residual equals 0. See, as we mentioned that all the total sum of the sum or the average of residual would be 0 all the time. I mean, this is the word box plot. See, that's the box plot. The vertical box plot. These are whiskers. See, you know the box plot. You have done box plots at a certain point. See, this one is the minimum value. These are whisker, and go and hit on this the bottom of the box, which will represent the quartile 1, Q1. And this line, which is in the middle of, there's a line, which is the quartile 2 or the median. And the upper box, this one, this boundary, called the quartile 3, the end of the whisker would carry the maximum. So you have a minimum, Q1, Q2, Q3. Q3 means quartile 3, and maximum. Those are, in another way, called the phi numbers. Phi number summary, graphically represented by the box plot. Box plot can be drawn vertically or horizontally. Okay, in the middle, not in the middle, somewhere you have the median, and then mean should maybe somewhere. Okay, mean maybe somewhere. And if you see this spread out like this, see, that means all assumptions are satisfied. In the same way, this residual versus height, if you see this kind of a pattern, see, they were going off like that. See, this going to fit in this kind of line. That means non-linear model. See, this will very clearly say that one. And here that will tell that one too. See, that kind of a non-linear pattern. This regression will fit in into some kind of like a parabolic shape, rather than we saw in one of the examples in that number of calls versus that the number of months being in the job, that example. Some kind of thing. Or from this one. And if you see this kind of a rising up and going down, that means definitely there's some kind of a massive violation of that these assumptions. When they were violated, you have to remedy them. There's no way you can, if they were heteroscedastic, you see, heteroscedastic means the variances are not the same. Hetero means not the same variances, unequal variances. If they were same, we call the homoscedastic. Same variance, homoscedasticity. Okay, homogeneity. See, so that one. But here they were more heteroscedastic. If they were heteroscedastic, how to tackle the model? You have to check all these when you have a data in your hand before you're going to fit into the model. That's the key part. You cannot arbitrarily get the data and then do the data mining, no, that apply the machine learning, no, deep learning, those things. No, you cannot. You have to go through all these if you want to come up with the best results at the end of the day, or like a very clean work, or like a very solid work. You have to go through all these. That's why we have to lay down a good foundation at this stage and see that by looking at graphically or mathematically or statistically, we have the procedures to get this done. So see, this one we can remedy. Then we cannot do this one. We can do some kind of a transformation to remedy this situation. Or there's another kind of a framework, whatever that we are working on right now, statistical framework called the classical framework. In addition to that one, there are 4 or 5 frameworks in the statistical arena called the Bayesian, non-parametric. For non-parametric means you're not going to use any parameter, no distribution, nothing. Okay, based on that location. Okay, that we can do the thing. Semi-parametric, fiducial, generalized, so many parametric uh, frameworks we have. But we are, if you're gonna stay in the classical framework and try to remedy this one, you can do some kind of a transformation. As we mentioned over here, box talks. And remember at a certain point, see, transform Y is the violation of constant variance and the normality assumptions. See, if they were violated, you transform Y. See, use box talks to come up with the best transformation of Y. Then the box talks will tell you what would be the best transformation. Then you were wondering that what would be the best transformation. That's another thing. Okay. So kind of like I'll show you a little bit real quick something for you on the knowledge. Okay, we're not gonna do in detail anything, but only for your knowledge, I can talk about. Let's see if I can pull that out. That's the one. That's okay. But box talks will decide what kind of a transformation you have to use, like Lin transformation, inverse transformation, or different kind of a transformation. But as we said over here, we can remedy those. Okay. So look at this example that we have a 20 telemarketing employees, average calls per day, 20 work this month on the job, telemarket 6. We got this one. See, you can see there's some curvature, but it masked by the more obvious linearity. It is masked, but still you can figure out that you can remember that how we tackle this one. See, later on we fit it to this one. See, residual from that one, you get the residual versus that one, and see how it works. So let me see that whether we have this one on chapter 600, chapter 6. We have that one. We have the data here. This data, I think, is telemarket 6 data. So when they run this one, they saw R squared, this one, the B naught value. It's the regression equation, but they fitted, they went to the residual versus one, not the Y versus that one. That residual versus one. And they saw this kind of a shape. That shape tells us, see, this should have a nonlinear term should be in the model. That means you can easily add the x squared to the regression model. We did that one in our examples that we did that one previously. I think with this one already we tackled the same thing, even though they call this one under the chapter 6 telemarket 6. We did this one under another chapter, telemarket data. Together this one, the test of lack of fit, the residual contain the variation in the sample of Y values that is not explained by the Y hat. This variation can be attributed to many things. Natural variation, omitted explanatory variables, incorrect form of the model. They say the residual contain the variation in the sample of Y values that is not explained by the Y hat equation. The residual means the error cannot be explained. We had that discussion, error, unexplained error is the key part. That one due to what? Natural variation. See, the variation can be attributed to many things. That variation of the error not gonna be the same from sample, sorry, point to point. See, variation in the sample of Y values, that is not explained by the Y hat equation. See? Y value not gonna explain that, see, Y values of this one, the variation in the sample of Y value cannot be explained by the Y hat. See? See? So this variation can be attributed to many things. Natural variation for random error, omitted explanatory variable. Some variable have been omitted. Incorrect form of the model. So, if non-linearity is suspected, there are tests are available for lack of fit. not the Minitab in SAS, we have those things. Okay, we can, yeah, that's how that we're gonna do. Mainly that, yeah, the rest would be that something. Let me see the test of that one. I can go and see. We gonna, I'm gonna skip that one for the pure for time being, and then we move on to this one. There's the forecast one. On this one, I'm gonna come here. Get this one. See this one. Test for the normality. See, test for the normality. How to check the normality. Several format tests for the hypothesis that disturbance area normal versus non-normal. These are often accompanied by the graph which are scale that the data which are normally distributed appear in a straight line. See, okay, normal score versus a standardized residual. Normality plot for residuals. See, standardized residual, and it's normality assumption. See, normality plot. See, probability plot. For these plots, see, normal. This is your weight versus this one. This is a scatter plot. This is the theoretical quantile versus this one. See, here you have the weight. Weight versus this one. See, okay, they were consistent. If they were normally distributed, I'm talking about the error, okay? Error. This is error. Normally distributed. That is same as that having that all the normality assumption being satisfied. And it is also being checked by the this. You have an error. See, error versus is theoretical quantile. No, can you remember? It's a error. Right. Yeah, see. Yeah, normal score. So the quantile, how to calculate, we saw that on how to calculate the quantiles here. At a certain point I showed you over here, but you don't have to worry about that. And when we run that this graph, they will show you pretty much everything. So X here means like a no, we're not gonna draw this one for X, we're gonna draw this one for error term, okay? So error term is gonna go to this one. Here, this one. This is the major one I wanna just pay attention on, and then they will go like this equally. If they will go like this, right? See, left skewed. This one left skewed or negative skewed. They go like this, your graph right skewed. See, like this, and go like this. This one go like this. They were can be seen over here in the scatter plot as well. Okay. More above this one, more above here on this side. See, and more above here. See, that's why I say more are scattered here, here, more are scattered on this side. See? So this is in the quantile plot. You can see that one. So let's see that. Let's see. Let's get this some data. Let's run this one and see. Okay, we have the cost and the number of ports for that telecommunication data. So we get the test for non-linearity. Okay, we can talk about that some if you want that the variable that some kind of a see. Look at univariate. I'm gonna run this one. And then I'm gonna draw a smooth curve scheme in the top of that one. See, if you want to get like that, see, you have a histogram. This is the histogram. See, for the cost, for the cost has been this. See, the overlay by some kind of a smooth curve, smooth normal curve. Then you're gonna go over there, histogram, normal. You give the mu. Mu, you gonna say estimate. That means we were pushing him to get the estimate of the mu, which is y bar. That means the average cost. Get the average cost. That's why we were telling here. In order to draw this normal distribution, normal curve, you really need these two, mu and sigma, which are called the parameters. Within this thing, these are parameters. Within this parenthesis, we have the parameters. What are the parameters? What is this one? Mu. Mu is that mean value. We don't have a mu. We have its estimate, which is y bar, which is the cost bar. Cost bar. Sigma. That's what we were looking for the standard deviation of that given data. We don't have for the population standard deviation. That's why we're going to looking for this estimate. That means standard deviation of that. Then histogram. That can be utilized in order to come up with that some kind of that bell-shaped distribution overlaying that given data or the histogram. Okay, then we can draw what box plot, horizontal box plot, see, H box. If you put V box, you get the vertical one, see, or V box for the cost, and from the we can get that one through the category, through the type too. Okay. So here for the cost, this is the maximum cost. This is the quartile, third quartile, second quartile, first quartile, and minimum value. Minimum cost, first quartile, the 25th percentile, 50th percentile, 75th percentile, maximum value. This is the mean value, average cost. You can graphically represent these 5 numbers. 1, 2, 3, 4, 5. These are called the hinges. This is the lower hinge. This is the upper hinge. And this line is the median. And this is called the Q3, Q1. This is Q3. Q3 minus Q1, interquartile range, this length of the box. And since we don't see any unusual observation, I'm gonna take that the end of the upper whisker is same as the maximum. So does with this guy. End of this lower whisker would be my minimum value. If you have any unusual observation beyond that point, your minimum would be the last one. But, and on this side, the same thing, your last point would be the maximum, but minimum or maximum never being considered as outliers. And the whisker gonna stop here. That means whisker, end of whisker is not necessarily to be the end of the minimum or maximum. It depends, okay? It depends. So graphically, you can see those things, outliers. How do you get the end of that one? By taking the IQR, this length, you're going to multiply by 1.5, half of 3. You can remember, if you go to this graph, the graph that we had earlier, the histogram graph, you can divide all kind of this thing. If you go to the center, you can have up to here, maximum can go only 3 standard deviation to this side and 3 standard deviation to this side. Then that's why altogether we're going to call this going to cover the 6 sigma. 6 sigma. Sigma stand for the standard deviation. So when you're going to manufacture something, that everything has to be within 6 sigma. Most of that chemical, mechanical, electronics, electrical components they made with the aid of the 6 sigma for that quality control, they were using this distribution. And then they say that that their error must be within a certain range, but the maximum range should be minus, 3 sigma on this side and 3 sigma on that side. So like that. So that those things, the outlier you cannot detect on this one. If you cannot detect, you can go to the box plot and detect. How do you get that one? You're going to measure that 1.5 IQR, that 1.5 IQR, IQR multiplied by 1.5, and then that length add to this from the hinge to that one. Sometimes it's going to go and stop here. See here. Okay, now we're going to start. Anything beyond that would be outliers. And the same thing over here. 1.5 times this length. Okay, go to this one. We got the 1.5 for certain reason because we have a 3 to this side, 3 to this side. You got the middle one. 1.5 with the 3 half of that one. That's why we get the 1.5 times. So you get that the bound here. Anything below is the unusual observation. Anything beyond that one, unusual observation. Like that, you can get this done like vertically, horizontally. See? You can get this one like a put it panel as a panel too. See? So horsepower versus type. See, for various type of vehicles. See? Foxtrot you can do. Horsepowers of cars. See? Type. Horsepower cars by type. Make BMW, make Buick. See? This one, see, pure and then Audi. See? Like that. So you can get this done any way you want. See? Those are see? Foxtrot. Can compare and contrast. See? Here, e-box. Test of the non-linearity. You can check the non-linearity. See, these are the graphs we were talking about, diagnostic test. Look at those. See, I need the regression, this one, model, cost, and the number of votes. We need the plot. R student versus the T stand for the predicted value, okay? Predicted value. This one for the residual, R studentized. See, R studentized means like a, you're gonna standardize, okay? Studentized and standardized, pretty much the same thing. Only difference studentized and standardized is this one. Here, you put population standard deviation. If you put here sigma, that's standardized. If you put its counterpart, it's a sample standard, it's called studentized. Another way that to make it more clear, if I draw this one and then say, I'm gonna say it like this: ZE divided by E over, not for this one, for anything, okay? It's not right. It's disconnected. Let me see. It's not right. Oh, but anyhow, that yeah, I'm gonna get rid of this one and then open up again. While we are doing that one, but I'm trying to say that the student type means like a standard deviation. You're gonna based on the standard deviation standard. If you have a population standard deviation sigma, that's called the standardized. If you have a sample standard deviation, we utilize in order to calculate that z studentized. Okay, so you get this one. Then the plot cost versus number of votes. Okay? Cost versus number of votes. You can get that one. Let me see whether we have that one. We have that one, cost versus number of votes. See, we have that one. This graph. And we have that we were looking for our student T. If you want particularly for those ones, we can easily get that one too. See, cost versus number of votes. Again, another way you can check whether that regression line. See, studentized what predicted value. This one I'm talking about. This one. See, that graph, studentized versus dot predicted value. T stand for the predicted value. They were distributed like this. And plus quantile plot. See, look at quantile plot. Look at how it's going to go. Residual versus quantile. See, residual versus its quantile. You can remember we were talking about that one here. Residual versus quantile. Residual versus quantile. See, if it were like this, skewed, do we have that kind of a shape here? See, go like this, or they were properly distributed. See, see. On the other hand, residual histogram, see, look like a L-shaped distribution we can draw for that. So all this you can that very carefully observe and then make a decision. See, if it were like looks like that is sometimes look like some see, unusual observation. If you're not going to take into account this one, this look like fitting into like this line. See, equally distributed above and below the line. But if you take into account everything, look at this one. See, like that, it's negatively skewed sometimes. So if they were violated, but still you can get this done because that assuming, that's why we assume that the assumptions are satisfied. We're gonna see whether the assumptions are satisfied. See? So the residual versus predicted value. You have to have a shape like this. These unusual observation come and then see if they were equally distributed above and below, then we can say assumptions are satisfied. See, residual versus predicted value being utilized to check what? To check what? Residual versus predicted value. See? Residual versus not this one. That's not the predicted value. See? Residual versus predicted value would be checking the constant variance. Residual versus the x value predict the constant variance and linearity. Residual versus the normal quantile, which is that we were talking about here. Residual versus the quantile. And again, we looking into three types: normal, negative skewed, right skewed, based on the shape as well too. So the residual is a key part here. Residual, here quantile. How to get the quantile? They had done the quantile for that one, but how do you calculate the quantile? We check. We had that discussion too. See, how do you get the quantile? See, we're talking about how to get the quantile. Yeah. Arrange your error terms. Okay, error. Okay, Excel, not the error. Error. Okay. Calculate the error if this is related to error. Okay, we are not talking about the Excel because we are trying to draw the probability plot or the residual plots. Okay, these are for the residual. Then got the C-score. Plot your X value on the horizontal axis and the C-score, which is called that one. See, residual and the quantile this way. So see, that one theoretical quantile on that side. X value, they're going to put the X value on x-axis. They have changed that one. That doesn't matter. Anyhow, they have to have this kind of a shape. So they're fitting into this one this way. It looks like a negative skew. If you go this way, positive skew. If they were equally distributed. But at this stage, we are not looking for that in large scale. Anyway, let's just get like a rough idea how they look like. See? So that in order to check that one, you need for the non-linearity. Here, mainly I'm focusing on the non-linearity. We'll check, see, non-linearity. See this one or this one. How could you gonna graphically check? That's what we are trying to do, like this. Non-linear residual versus the predicted value. You can use that one. Residual versus the predicted value. Residual versus predicted value. We'll check the non-linear. get the linear. So, so I'm sorry that I'm looking for this one. Okay, residual versus the predictor value. Okay, residual versus the predictor versus residual versus predictor value. This one. I'm sorry. This one. See, that's for that one. See, that's the one that I'm. These graph gonna come along with the regression. Okay, when you run regression, those graphs gonna come along with that one. Okay, when you have that one, in order to check the linearity, do you have the residual versus the predictor value? I don't see that one. Residual versus predictor value, I don't have. Residual versus the X value, I don't have that one. That's why I ran this code to get that one. See, I ran this one. I said, give me the residual versus, for the residual, you can use the student type residual, doesn't matter. See, residual versus this one. I need the number of ports. This one I need. See? To get this one, X value. See, predicted value. Then the predicted value, let me see. For the nonlinearity, residual versus predictor value, not it should be predictor value. See? Yeah. This one. See? This graph, I'm eyeing for this graph. In addition, we have a residual versus predicted value. It's come along with that one. See, come along with this one. P stand for the predictor. See, let's run this one and see. Homozygosity. P. Okay. We're gonna run that one. R means residual. Okay. R means residual. Okay. Those are come along with that one. Okay. What I mean. See, predicted value. This is what I specifically looking for the predictor value and predicted value. Let me see that P stand for which one? Predictor value. Number of ports. Okay. This one. Residual was the number of ports. We came along this one. Let's say that, okay, I'm gonna do something. I'm gonna get rid of this one and run this one, okay? And see what are the graph gonna come along with this one. Okay? Let's say the extra one first. When you run regression, we normally see some set of graphs. Okay, they come here. Okay, they have this one. Residual versus X come along with that. Okay, we really need the predicted value. Okay, that's why we're gonna add that one. Yeah, so P stand for the predicted. And C extra one gonna come this one. So I'm talking about this one, the one, not this one. This is the second one. This is related. This one, cost over this one. I'm talking about this code. This one versus predicted value. See, they were distributed like this, that they will satisfy. We can check that one with predicted value graph. Can you remember here? Residual versus predicted value graph. We had this one here. Residual versus predictor value, this one. But I think nonlinearity check can be even checked with that one too as well. So this should be nonlinearity can be checked through the residual versus the predictor value plus the residual versus this one too, predicted value as well. Mainly residual versus the predicted value you check to find the constant variance. So that means this one here from this graph. Yeah, we have a predicted value. No, we don't have that discussion here. We don't have a predicted value as well. We have this one to this one to x. So this one, I think that's the normality, that's the independence. But this one, in order to check the linearity, we don't need this one. That's that I think. This is more than enough. Residual versus x, it's same as this one. Okay, but I'm gonna say this one and extra one. Non-linearity can be, see, this an extra one. Okay, this one extra. But residual, so sorry, this one, residual versus x, residual versus x. Residual versus x. Residual versus x will be enough for you to check the linearity as well as the constant variance, both condition. This one, which come along with that one. What I did was I added this one to get the predicted one as well, because in that one you can use to check both at the same time. If you use the the predicted one, you can check the constant variance only. This one variance only, but it's similar to the residual versus x value as well. This is nothing but residual versus y hat. Okay, y hat. This is residual versus x. They both would look like the same. From this one, you can check the linearity as well as the constant variance. From this one, you can check just the constant variance only, not linearity. Constant variance only. Let's take this one. See, residual versus predicted. That's why I'm using that one again. See, I use the R and P. That's the same thing we have done earlier. See, R and P. See, R. See, asterisk and P means like R dot. They will mean that's the plot between these two. So R and predicted value. See, this will can be utilized to check the homoscedasticity. This can be utilized to check the linearity. Okay. So here that if I use this one, actually that you can check this one as well over there. So this one copy and then and both can be checked with this discussion and homoscedasticity both from that graph in the way that we do over here. But if you really want to check only the heteroscedasticity or homoscedasticity, you can say predicted values. If you want, you can run and see that this one's a test. I'm talking about this curve. See this curve. Okay. This pattern is going like this. See? If they were going like, let's see that how could we gonna see that non-variance? If it is in a like a funnel type, okay. So this is what I'm trying to say. This at the same time, I'm gonna open this one too. This one go like this, getting see larger and larger. See, this is x. See? Larger and larger. Then this become non-various. But here we don't see any funnel type that much. See? Look at they were like a thing. They were spread out above and below through a certain band, not through like a funnel. See? This funnel type, the variance is going to change. Okay, that's another way to have a look at it and check this one versus x. You can check that one too. There's no funnel type like I gave it, except for this unusual observation. These are going to be on see, some kind of a band. So these two can be utilized. See, that's what the heteroscedasticity. So the normality you can check with that one. See, the predicted value, see, and the residual, see, residual for R. Okay, let's say that this one, restaurant. number of ports. That's the same thing that we normally get. And then you can run so normal test on top of that. You can get this one different ways. QQ plot. If you really need to get that plot only that separated, you don't need it because it's already come along with that when you run the regression. But if you don't want to run regression and just focus only on this one, see, we got that one separate residual versus the quantile. Quantile, see, normal quantile. How do you calculate the quantile? We check that one. Okay, how to calculate? This is the way how you're going to calculate the quantile. We discussed that one. See? How do you calculate this one? See? You get the your residual, you're gonna order, and then you're gonna get that it's corresponding this one, and correspond to this one, you're gonna find the z-score. That's called the quantile. It's the residual. They are residual and it's corresponding to residual quantile. Standardized quantile. Sorry, standardized residual in another way. That graph you can get by the QQ plot. See, from this through this. So let's say that this one kernel density equation. That one. They were giving like some kind of something not related to this one. You don't have to worry about that one. I don't want to go detail on that one. Just I keep that one like that. On the other hand, if you want to check the independence, as I discussed over here, independent can be checked by the residual versus the order of observation. So that can be done even through this one. Independence. It's the order, it's the residual. That's the same thing, but the same thing we saw earlier, see. But this has been done by order, by which way observation come in the observation order has been taken into account or check the independence. If they were fitting into again this kind of like a band, they were independent. If they were going like a funnel type, again it's gonna be a non-independent. I don't think that we very rarely see that kind of situation. See? Number of ports, residual versus the number of ports for the cost. That plot. Another one. This is for this one. Let's think that's the same thing being reproduced 2 times. So those are the kind of like get a rough idea how to check that using the plots. You have the plots. If you don't have a plots, you can use in these all the codes. You can get that you check that independent heterozygosity, nonlinearity, and the normality. Roughly, okay. I don't want to go too much detail on that one. Okay. So with that said, let's move on to that the next one and then have a look at some homework too. See, in the chapter 7, pretty much what we're gonna do, we're gonna include a categorical variable for x. See, if you have a categorical variable, that categorical variable, how do you represent that one? Let's say that same way like over here, that example I had, I'm gonna open while this is opening. Can you remember we have 3 categories, and then if you have 3 categories, and then for the any so far up to this point, x variable being been that kind of quantitative, okay, not numerical. But now on, I'm gonna add the categorical variable for that x-axis. X would be some kind of a group variables like a gender, male, female, and the height being categorized Rather than giving the height numbers, you can easily categorize and say short, medium, and tall. These three categories. Income, rather than giving the income, you can say low income, medium income, and the high income. Or that family size, number of people in the family. You can talk about the number. You can talk about the number. Rather than the number, you can talk about that the small size family, medium size family, and large family, or like that. So like this for that size. Showing earlier one of the example. See, on y-axis we have some kind of variable. Let's say that here we were taking about something called the data diet versus no, the graph. I mean the graph. And the y. Yeah, not that one. Not that one. Not that. Yeah, yeah. See. So I have a y-axis data diet. For the x-axis, I have a non-smokers, the former smokers, and the current smokers, smoking status. See? So these are categories. If you have a category, how could you gonna fit in this into a regression line? See, we still can fit in into regression line. That's called the categorical regression or group regression. You have done group regression in that you're 605, 600 in large scale. 600 analytics 600 we were discussing in large scale, but using R we were discussing that empty model. Can you remember that evolution of these regression models? You can remember. So in the very beginning, you had the empty model. Can you remember? You had the empty model. On this side, you have a Y. Here you have a nothing on this axis. Nothing. So that's why you utilize Y bar as your model. Can you remember your model would be what? Model would be data is defined by the model plus the other stuff. Other stuff here means what? Error. Data is Y, model is Y bar plus this one error. Sometimes here Y bar is denoted by Y hat plus C. Same thing. Or B naught plus C. We had only B naught only in empty model. Plus one empty model. Empty model. Empty model, this is the model. See? Or this one. Or this one. Same thing. Y bar is nothing but the grand mean. Grand mean of Y. See? Grand mean of Y. Then later on we did the number 2, the group model. Actually, we did the group model earlier than the regression model. Group model. Group model. Or sometimes we call the categorical model. That's the one I'm trying to do right now. But rather than do this one first and get into the regression model, which seems like in this class we were doing regression first and then come back to categorical again. Categorical model, or we can call this one analysis of variance. We can abbreviate it as or give an acronym ANOVA. So what that means in that one, instead of using that nothing, we started introducing some kind of a thing, categorical variable for this one. See, we introduce a categorical variable for X. Yeah, definitely this one is quantitative. We know that one. Okay. Variable. For my convenience, I'm going to put this one cont, this one cat. Can you remember? Cat variable. So then we have what? See? Let's get that example. Non-smokers, former smokers, current smokers. See? See? Never smoke. See? You can say the never smoke. And this one, see? Former smokers and current smokers. And this one, let's say for this one, they get something called the data diet, some kind of experiment they were doing.
So if you go to this one, you can get the mean of this guy. So y bar of ns. You can get the mean of this one, y bar of this one. You can get the mean somewhere, y bar of current smokers. So how do you write the model? How do you write this model? You're going to say your model, you're going to say data being model by model plus other stuff. Other stuff always data means y. How do you write the model? B naught plus B1, X plus error. But X has what? In this case, three options. Since we have a three options, let's say that in a case you have a two option, you have enough one. I need another variable to represent three variables. I need at least two variables, two dummy variables to represent three variables. So I'm going to add another one here, B2 X2 plus P. See? So those are called the dummy variables. Dummy or indicator variable. They were used for the purpose of just calculations only. They were not real variables. They don't represent anything at all. X1, X2, X3. Here you can say this value, see here, you can put X1. And then you're going to take this one to represent three things. One is what? Non-smoke, never smoke, former smokers, current smokers. So here too, represent former smokers, current smoke, never smoking, NS, FS, former smoker, current smoker, CS. Now we have to make sure X1 represent that the B naught here, there's another one. One of these levels, I'm going to take as the basis, as a foundation, or as the base. Okay. If that's the case, you put the 0 for that one. If you really need that one, this will represent that one. See, this will definitely represent what? NS, never smoke or non-smokers. So this one, if you need this one, you put the 0 for this guy, you put 1 for this one, you put 0 for that guy. Then if you really need the second one, the people who really that the currently smoking, non-smoker 0, former smoker 0, this is 1. So you're going to assign some kind of a number for that one in order to get the calculation. Those are the dummy variables. See, this one NS, when you plug in, if you say you need the NS, if you need the NS, non-smokers coefficient, you put the 0 here. Because this is not for the non-smoker. This is for the, this will carry X1 represent the former smokers only. X2 represent the current smokers. And which way X variable going to represent the NS? You don't need one because I have taken this one as the base. When you run that one, you get the B1 and B2. B1 and B2. B1 and B2 are what? They are the values. See, if you run this one and then get the X here, Y here, you run that one and get the, okay, this is your Y bar of non-smokers is same as B naught. See, B naught value would be that. Let's say that next value, somewhere here, Y bar of the former smokers. And this gap between those two represent B1. When you run regression, if you get the B1 is the difference between those two means. See? And the third one, let's say that somewhere here, it's not necessary to be like that, Y by current smokers. So this gap with respect to B naught, not the B1, not the second one, B2. That's the gap. See? Those will represent when you run regression. If you put those one, they will represent that. So here, let's say that with the aid of this SAS, how we gonna do that one? This is for the non-smokers, so never smoke, so former smokers, current smokers. So now we use that these are smoking status. So you see categorical variable smoking status. It's categorical. The other one quantitative question. So far, for XE1 that we use the quantitative variable all the time, weight, height, so you see all the time numbers. Even the numbers you have, as I mentioned earlier, let's say the age, you can divide into three categories. You can categorize. You know how to categorize. We have that training. See, we know how to categorize. See? We know how to categorize, and we know how to change the data, the names of the situations. See, let's look at that here in the chapter 7. One for time. I'm going to get rid of that one. So 7. I don't need the 8 for time. 9. See, that's the same thing they were talking about here. If you have a 2, you go to 0 and 1. If you go more than that one, you go to just two variable. Look at in the very beginning, they have only one variable. See, the Harris 7 contains information on the salaries of 93 employees of the Harris Trust and Saving Bank. They were sued by the US Department of Treasury in the 1910s. Here we examine how salary depends on education. Education. See, Harris salary, Harris data. Okay, let's get this data. That will contain what? 93 data. They will contain salary, education level, how many years experience, months in the working months, and the male, female, or male. Okay. So if you have that one, see, I'm gonna recode first my gender. Recode, sorry, the gender I'm gonna, can you remember we have see males. They call the males, okay. They call to the male gender. See, males, you see, gender has been named as a male. 0 for the let's see, 0 for female, and male have 1. I'm going to change that one to easily distinguish that one. You can change that one. Okay, you're going to set data. See, you're going to set this one to this one. Okay, so you get the data, and then you're going to set back to that one. Okay, you can see length. If you want, you can store this one in different place. Gender, see, that's like a size. See, 12. Males, I call them males. If male 0, then gender is a female. Else, if males is 1, then gender is male, or else gender is empty. Or you can do like this way. See, sex upper. If you want to change the uppercase and lowercase, see, that's a different thing. See, you change that one. See? You know how to change that one. So now we have a new variable called the gender. See, gender. We're gonna check other new variable. Gender with this one, this length. Early name is males. Males has been changed to gender. Not only that, I did the 2 things. I changed the name of the variable as well as the level of the variable. 0 to female, and change that one to gender, and then change that one, the level 1, and not other level as well. So that's why we have everything today. Now we call that one gender. We can easily distinguish females and males. Whoever has a 1 male, 0 female. So once you do that one, you can print and then looking into the data. So since we know that, and you can get the table, frequency table. Let's say that how many from each one, each group. See, if you need the frequency table, how many from each group? See, female 61 as a percentage, cumulative 61 and 32, males and female. You can get that one, and then you can do the scatter plot. See, the salary versus education. Okay, by the gender. Is there any discrepancy between the salaries of that between males and females? If you want to check something like that, you're going to do that scatter plot. Y versus salary versus education. But education, keep in head, education is
categorical, not numerical variable. Okay, let's see what's going to happen. These are numeric. These are numeric. But since they were that there are certain number of that very few number of options for that one, you still can consider this one as a categorical as well. We had that discussion at a certain point. These are numbers. Now you can say these can represent like categories because you have only like a very spread out that data points for that particular variable. See, education, how many? 8 or 10 or 12 or 14 or sorry, 15 or 16. So because of that reason, there are few number of options for that particular data, particular variable. You can consider this one as a like a categorical as well. Or since it has a numbers, you can say quantitative as well. Doesn't matter. But you can easily see that they belong to that categorical type. It has been done by the gender. You can see very clear cut, even though that same number of experience. Okay? Males, they were getting a higher salary. I don't know for what reason, but see, they have that same experience. So this, if you see this kind of animal to be remedied, it has to be remedied before we're gonna remedy. It's not up to us, but they are that the corporations or whoever that responsible for that one paying that salary, they will take care of the business. But as a statistician or data scientist, that's your duty to that make the recommendations. See, recommendations for them and say this. We see that on our observations. Our observation you can that to provide to them, so you can see clearly by doing this. As I mentioned, you can this one take as a like a categorical as well as quantitative. Okay, not the female and male. Okay, for sure. So the other one, scatter plot and regression line of the mixed model by gender. Okay, we can go to the scatter plot and let's try to get the regression line. See, okay, very clearly see that males the salaries are higher than that of this one, regardless of their experience. Sorry, the education, the how many years they've been on school or college or being in the education. Can you see? Can you see? Then regression analysis do for the regression of this one. See, education and the males with the males. See, okay, look at what we got. Take all the males. Did I put the males here? See, males. If you want, you can put the gender. The males. See, I'm gonna add the education and males. Males will be taken care by what? How? So that's the part that we were talking about. Let's say that here, see, we saw that one. See, and since I really wanted to get exactly the same one, I used the males. Okay, so we had the same result. See, then if you really need the value for that one, an indicator variable bj is not really a slope. To see this, evaluate the equation for the two groups. See, if you need the females for the gender or for the males, put 0. This is your equation. Salary hat equals hat, okay, equals B naught. Already we got that one. See, this one. This is the B1, is the B2. The males. B2. Now you might be thinking why B2, why for this guy, why we not gonna have a like another one? Because this one has only 2 options. This is categorical. You can consider this one not like a categorical. You can consider this one like a numerical, okay, for time being. Okay, for time being numerical, but this one categorical. It's a mixture. If it is categorical, if you have a 2 options for the male, for the females, you put the gender equals what? 0. If it is gender, males, 0. Then you're going to come up with this equation. If it is female, sorry, if it's male, you put the males 1, like that. Then you can easily see their slopes are the, see, indicator where vi is not really a slope. See, v not the slope, but the slope, real slope, you can see after that. See, this calculation. See, look at it. Their slope 80.7, 80.7. They should parallel to each other. See, but on our one, we don't get that one for certain reason because there's an interaction term. Interaction term. When we were running that one, you saw that. Okay, here we're gonna say that scatter plots of mixed model. That means categorical and quantitative vary by gender. Okay, if you run this one, so that's a scatter plot. Sorry, that we can go to the next one with the regression line. Regression line. Eventually, they should not be parallel. Parallel means there's no interaction. But this seems like they were not parallel. They were having an interaction term. We're going to talk about that one too later on. See? But on their slides, they say parallel. That's okay. For time being, let's take as this one. Males and females. But how do you get the equation? By doing some kind of adjustment, okay? Some kind of adjustment. This means this is what we were doing over here, okay? We were thinking, I have a data, okay? I have a data being modeled by this particular model for the other stuff. My data is y, okay? Model is nothing but, I would say b naught plus b1x, okay, x1 plus b2 x2 plus e. I will explain this one. Y represent salary. Okay. B naught is B naught. B1 is B1. That's the coefficient of first variable. It's the education. Educate. But remember, this is quantitative. I'm going to take that one quantitative. This is also quantitative. If they were quantitative, you don't have to have any, you don't need the dummy variables to represent it. B2, X2 means here the gender. Gender means they use the word males. Okay. Male has 2 options, either 0 and 1. Okay. If it is 0, that means X2 can take 2 options, 0. If it is 0, females. If this one, male. Males is the word that has been utilized in order to represent the gender. Okay. Like that. That's why we're not going to go ahead and then put another, you don't need another dummy variable like x2. X2 is a dummy variable. That's what I want to tell you. There's one dummy variable enough for you to represent a certain categorical variable with 2 options. If it has 2 options, 1 is enough. If it has 3 options, we need another dummy variable as well. This is not a dummy variable. No, this is not a dummy variable. Not a dummy variable. It is a real variable. A real variable. It's not a dummy variable. At the end of the day, if you need the males, you really need to put that 1 to this plugin. The x1 should be replaced by 1. That's the technique. If you need this one to be that, if you want to find the salaries for the females, you have to plug in 0 for x2. After you run this one, after you got the b naught and b1. Okay. Here we're not going to say that this is the base or something like that. Only b naught will physically represent what? When you don't have education, 0 education, that a certain number of years, 0 years of education plus that if they were females or females, this is going to go away, then you are left over for that one, B naught. So this has been set up for the female. If it's a male, this has been added to this one. Say, let's say that the males, you have 1. That means this been added. See? That's why, see, this part for the females, females, this part is gone.
So it seems like this value you see in that one is the average of the female salary. See, average of the female salary being added to, see, based on their education, see, this much. This much means what? For extra year of education, he's going to have a salary increment, sorry, salary, see, more than the people who had like us that zero education. See, it has gone up. See, every time you have 1 year education more than that the extra that 1 year's that experience, 80.7. That's the same thing for this guy. Doesn't matter regardless of the male or female. The slope would be the same. The problem come here, the base salary. See, the base 48.65 here 41.30. That's the slope. Okay. This is based on that how much that education one more than the that up to that point, certain point that you have that and that's the slope actually. See? That's why that we're gonna add that to get the see at the end of the day. That so so let's see that this one over here. If you really need to get the data, our that salary that this okay our the model you're gonna run, okay. After running that one, you saw that what you're gonna get for B naught, B naught, see, B naught this much, B1 this much, B2 this much. Male has two options too, okay. So females as well as male because it's a categorical, it's a mixture. It's a mixture. This one has a quantitative as well as categorical for X variable. See? So then regression has a this one salary males and we need the slopes, okay. Oh, this is slope. Yeah, we don't have this slope. That's the same thing. So we have a calculator. This is slope. So the instead of that one, this is very interesting what we are trying to do. I'm gonna write the equation. This discussion keep going, okay? Then if you wanna check, after counting 4 years of education, there's no salary difference between the males and females. After counting 4 years education, there is a salary difference. How do you run that test? By looking at what? Our p-value. There are p-values. So which p-value we looking into? See, that's why we say you looking into the beta males. Which one you looking into? That guy. Okay, this is the one that you take into account to see whether if you have a question like this, for accounting for years of education, there's no salary difference between the males and females. If you want to check and see that the education has been taken to account, that means this is fixed. You're not going to go ahead and look for anything on this one. Education, you don't have to worry about it. It has been taken into account for both parties, males and females. But if you want to see their salary are different, you run this test. You check this one whether this one is equal to 0 versus its counterpart. If that's the case, you have to go and looking into its p-value. See, its p-value, which is 0. That means like we can easily reject H0. Reject H0 means you're gonna simply say there is a difference for sure. We saw that one already. See, we saw that one. But if you want to really convince that one mathematically, that's why we are running tests. Same like earlier, can you remember when we were just by looking at some graphical graph, you can make sure that the residual is going to satisfy all that given assumptions, but still I was talking about some kind of a statistical test for you to that verify that what you have seen. See, this one not enough. So scientifically to prove something, you have to run a test. The test is like this.
So you have to make sure you're going to take into account this one. See? Right, right. Because we focus only on the categorical variable. Okay. What if the coding was different? That means you're going to put the other way around. They switch those two, but still you get the same thing. That's why we have to say it doesn't matter. You switch. What do you mean by switch? You're going to say this one switch. I'm going to put 1 here, 0 here. Doesn't matter. You still get the same result. You get the same result. Same result. Okay. You get the same result. That's what they were telling there. The same result. Let's say that now you have a three options. Same thing that we were talking about in the very beginning. What? Non-smokers, former smokers, and the current smokers. Same way here. Now sales we have in 25 territories, advertising in territory, the bonus paid in territory, and there are 3 regions too. See, also region. See, region has 3 options. These are categorical. This is numerical for sure, numerical for sure, numerical bonuses, numerical advertising, numerical, but the region. How the region gonna affect? What happen if you just put it into the model? See, you run this one and put it into the model, you get this one, and the region, how is region gonna important? That's why in all, when you have a 3 of them, let's look at this one. See, this one here. Before I go to that one, I would like to explain the rather than writing. If I go to this model, okay, before come to the other example, this example, look at what I'm going to do. I prefer to write this example in this way. Salary equals B0 plus B1. You can easily get the B1 by running regression. Education. Instead of putting the main B2, see, B2, instead of putting this one, I prefer to put one of these levels, not the gender, not the males, not the males. Let's say I'm going to put the one of the levels of that particular categorical variable. I can write like that way too. I'm going to say females. You can write like that way too. See? That's the kind of a discussion we have built in up over here. See? But actually for the, see, we mean one, males 1 to 1. Here it has been written in men, okay, in men, okay, rather than that one, I'm going to give you a name, men, because otherwise they get mixed up. I'm going to instead of females, I write that one with the males. Since I can write with the males, I'm going to say men. Okay? Men. With the aid of men, I can write that equation as well. Plus C if you want to add that more specific item plus C. So how do you do that? See? Look at what we do. We're gonna set up though. Okay? Males, then women. I'm gonna use the 2 words, men and women. For the males, see, they both are 0, 0. Again, males 0, then women 0. Males 1, then men 1. 0, 1 has been assigned for new people. I'm not going to call them that females and males. I'm going to call them women and men. Okay, that's why I used my new variable name men, because I'm using one of the levels as my variable. One of the levels as my variable. Or you can put the other way around. Now you can take the women in that one. You can write this one with the aid of women as well. Okay. But for the females, I call here for my convenience. See? Salary B0 plus B1, educate plus B2, I can say female. With the aid of women, I can write that one too. I can write this one in 3 ways. This way, or this way. Okay? B0, B1 educate, B2 gender, or they call the males for gender, or salary, B1, B2 that educated men, or it's the 3 years. But you have to set it up. If you want to run that way, you have to set it up. See, 0 and 0. See, males has been changed to women. Here in the very beginning, see women 0, then men also 0. Okay, this is the beginning, this is the beginning date, this 0, 0. See, or 1, 0. See, the male 0 we call in the beginning male 0 for women, females. That one I'm going to say 1 for them. And for the males means that the males 1 means the male for men. Men I call 0 now. Because I'm trying to use this formula. I'm trying to use this formula. I'm trying to use this formula. Look at 3 ways I get this done. See, and see whether we're going to end up with the same result. This way we ran all. Instead of males, we ran that. We have a 2 option for our categorical variable. You know, we have a educate males. That's good. Then we're gonna do this one. Don't see anything. And let's run our regression with data of men. Men. 4173, 4173, 4173, 80. Doesn't matter. You use the male, so 80, 70, 691, 8, 7. Then let's go and do the other way around. I'm gonna really like to express my categorical variable in one of the levels in males variable, which is women. Okay, so let's run this. See, educate plus women. See, 48, 64. See, now 80, 70, 691. 691. 691 from okay. This one, okay. This one 48, 64 because the intercept gonna change. See, these two things because of the negative. See, because this time they have subtracted. Okay, you know they're gonna get the same value, but negative. This one 80. That's the same thing. Educate not gonna change. This one's gonna change. Can you remember? You can remember that you are slow. This discussion. I'm talking about this discussion. Here. No, I'm talking about this one. 4865, you got that. If you put the other way around, you get the 4865 because of this. This will be added to this one. So they were consistent. This one 80, 80 is 80. Is the women slope is 692 here, negative because we put the other way around. In the beginning, it was like that. At the end of the day, it becomes like that. You see, look at this, right? In the beginning, this is not the real, this is what I have to tell you. If we, in this our whole discussion, this is not the real V naught. V naught has to be, make sure that after calculation you get this one, but if you have a 0 for that particular variable, it's going to be that one as well. See, not going to change. But you have change here, that's going to change to this one. It stays the same. That's the same thing we were discussing earlier. I put the men. When you put the men, instead of men, if you do this one, rather than you're not going to do the any I'm talking about this part you don't have to do if you set up like this. That's what I'm trying to say. If you set up like this, either this or this way, okay, rather than this way. I'm talking about the educated men, no educated women. You don't have to do this kind of a calculation. That will one shot displayed on here. You can see clearly. I was using the women in this case, okay? Women, see? Women is one, okay? When this women is one, you see that 4865 has been switched because we switched that one. That becomes negative, but this is consistent with this one. Consistent with this one. See, you don't do any calculation by hand, but if you run like this, you definitely have to do the calculation to get the real values at the end of the day. See? So let's see that whether, no, sorry, this one. Let me see that what it's going to show. $41.73. See? See? If you really need for that male or female, you don't know. Male, this one represent male or female, you don't know yet. But later on, you say that if you put the male 0, it should be same as that one. If it is for the men, should be this one plus the other value, which is 4865. See? You don't have that. But if you straight go to that one and say, okay, I really need for women to be included or men to be included, see? And you can get that value one shot. For the men, you don't need any, sorry. Oh. No, we don't do this one. Sorry. Okay, then I'm gonna run this one. So already there. But for the other one, if you run the other way around, you get for the women easily. But you have to run this one first. Okay, I'm gonna run both of them. I don't have to do any calculations. So already there. 4865. At 4865. You might be thinking it should be for the males. Why? Because we flip that one. We switch. We switch, okay? We switch. That's reason, okay? That's the reason. This is the reason. Women's here, men's slope become women's slope, okay? Here, see? Men's slope is now women's slope. Sorry, the intercept, I'm sorry, intercept. And this value being negative, earlier it was positive, okay? That's the same thing, okay? That's why you don't have to do anything by hand. So now look at this one. Now here we have three options. We have three options. As I mentioned in the beginning, that since we are planning to have the region, this option can be tackled by the some kind of a coding scheme. That means that for the south, one region you have to definitely keep as the base. As I mentioned that in the beginning, that in the three option category variable, can you remember smoking status? Never smoke people were kept as the basis. Other two were being coded. The same way here, if you really need the south, see, you're gonna keep the, sorry, Midwest as the 00. Other two, how you gonna coding? This one, if you wanna go and take two variable D1 is the coding is in the D1, represent if it's south should be 1, other two rest should be 0. If it is a west for D2, second variable, this is X1 and X2, okay? I'm talking about the X1 and X2, the same thing. 0, 1, 0. Okay, same thing I did here. Okay? Same thing I did in here in the very beginning for the non-smokers and smokers. See, look at what I did. I did this one keep as my base. This one as a base. In another way, this one here, the here that NS,
This one B naught will represent, that means NS0 and former people 0 as well as current smokers 0. If that's the case, what would be the value for the beta diet? See, here this one will represent this guy 0, former smoking, that people will be represented by this one. If that's the case, this should be 1 like that. See, that's the coding. It's the coding. That same coding, if I put to the same way like this, like that, see, like that, if I'm coding scheme, see, smoking status, I need that current one and this way and this way. You can say that this is non-smokers here, non-smoke, sorry, never smoked, current, former smoke, current smoke, in this way too. See? So this one I can write this for particular this one. If I code it like that, I'm going to go ahead and put here this one this way, 1, 2, 3 here. See, I can say smoking status. This one I need for, not the first one, I need for former smokers and current smokers, and the options, the never smoked 0, 0, and former smokers 1, 0, current smokers same thing. That's why I put this way 0, 1, 0. See, if you want, you can put this way 0, 1, 0, 1, 0, 0. Whereas the not the non-smokers 0, 0, 0 actually. If you want, you can add this one too. Here. See, look at. If you want to use the 3, that means the 3 options, not the 3 variables, 3 options, and say NS 0, 0, 0. So you can read this way, doesn't matter, or this way. See, CS means 0, 1, 0. FS means 1, 0, 0. NS means 0, 0. Or this way, 0, 1, 0, 1, 0, 0, 0. That's the same thing they were talking here. Okay, that's the same thing. That's the same thing. Now you can have the region. See, region being added to this one. See, look at it. I'm sorry, region being added to here. Okay, and they ran this one. They ran and then they saw this one. Let's say we run in this one and with the region and see we're gonna get the same result. Okay, before we're gonna do this one, I'm gonna use the code. Okay, sorry, I don't need that one. Okay, I'm gonna run this one shot. I'm gonna get the data and run that one. This one I have advertisements. Add see all. Okay, this one full one. Advertisement, bonus, region. Add and bonus, they were numerical. Now the region is categorical. I ran that one. I saw that I had bonus region. Which region we don't know. For the region we have this value. See, -84, 1.155. That's the slope for that one. 1.11 is rounded to that one. 118, 19. They make it a round number. R squared and everything we have. Now, if you need for certain region, the sales for certain region, look at what they did over here. See? The difference between the region 3 and region 2 is 190. This one also 109. What that means? Where's 190? You see 190? This one. They say the gap between sales between which region to which region? What is the base? That implies the difference between region 3, Midwest. Region 3 is that base, okay? And region 2. Or region 2 and region 1. That means that's the base. From any direction related to that example, okay? This is what they were trying to say. See? So you have this one. See? So this one you have a sales. You have a. I'm gonna take into account region only. Okay, other things. Otherwise, it's a 4-5 dimensional. The others are over here, advertising, and then bonus here. Okay, I'm not gonna take into account that one. I simply go to the region. Region. My base would be what? My base would be Midwest, region 2. Okay, Midwest I'm going to keep here for my convenience, Midwest. Okay, and then I keep the South here and West here. But they were telling, if you see average of this one, Y bar sales value, okay? Y bar Midwest and Y bar of South, Y bar of West. They say all the time everything is respect to this guy. The gap between this one is B1. The gap between this one is B2. That gap, okay. The gap should be B2. So this one, see how they wrote this one. See B1, B2, see B3. But the B3 has a 3 options, okay? 3 options. B3 has a 3 options. This one has a 3 options. So how their options were taken into account by, see, this guy, see, region, that will be the difference between Midwest to region 3, West, Midwest to, sorry, West to South, okay? West to South, the gap, okay? West to South. That means that this gap, okay? B1 and B2, that's different thing, okay? Under this one, you can, I'm not talking about this B1 and B2, that it's only that we have this one only. You can spread that into 2 parts, okay? That means this one. Okay? So you have a, like, let's say that your sales, and let's say you have a region only. See? Region only, you can divide this into Midwest, West, and South, like that. So that when it's come to the picture, if you want to write this one, you can write that with the aid of that. See, so like this way: the B0 plus B1 x1 plus B2 x2, like that. And that's for only that guy. Okay. So then x1, this B1 represent what? Midwest 0 and West 0, South 0. X1 represent what? X1 represent Midwest 0. Okay. West equals 1 and South equals 0. This one represent, let's say this one for the South. So the Midwest equals 0. West equals 0 and South equals 1. Okay. Like that. Only for that part. But they were telling us the gap between the West to Midwest and West to South, these gaps 119 and 190. That's what they said. Yeah, see, those are the gaps. See, that gaps. See? That's it. Implies that the difference between region 3, that Midwest to West, Midwest to West, and West to South is 190. Where is the 190? In this one, when you go to the region, this slope is responsible for that gap. See? This one. But this one, this is related to this guy. Okay, this is related to this guy. See, this picture, this equation has been represented graphically here. B1 is nothing but the gap. B2 is nothing but the gap between this guy and the Midwest and the West. This guy is Midwest and the South averages.
Okay, that's a different thing. But here they were talking about this 119 is the gap between Midwest to West. See, this one. See, this gap. So if the West in the middle, then West to South and West to Midwest. Okay, the way that I have drawn out here. Here, there, see, Midwest here. Sorry, West here, Midwest here, and South here. Southeast 109. That's the value represented in the equation. So what they're gonna do instead of doing like this way, they think about applying, okay, rather than interpreting that one and then get this value. See, look at that sales. You got the form. If you know the South, you really need to make sure that the sales, what are you gonna plug in for this one? So not for that guy. I'm sorry. This one, this equation. If you let's say that, how could you gonna know that the sales for the certain region from this one? How do you know the sales for certain region? What are you gonna do if you really need the sales for certain region? The way, let's say that South region sales, Midwest region sales, and the West region sales. Can we figure that out from this one? No, that only thing we know. See, use indicator. Sorry, see, use T. I'm sorry. This one. See, how do you use region? It's not see, like that. More flexible way because this one. See, this imply only this one only. They have a, like a the gap difference between the sales in the two regions only. The sales difference may not be equal, but this forces them to be estimated that way. But only thing we know, if you go in this route, the differences between the sales between two regions only. Other than that, you cannot make any sales. You can that thing that the standalone and say that okay, standalone regions or that individual regions cannot be talked about here. Individually, each region has a that how many sales we cannot talk about that one if you set up like this way. That's why they were looking for this kind of indicator variable to remedy the situation. If you do like this, you're gonna set up the way that I have written over here. See? You have to go in this route. See, that means if I write this one this way, I'm gonna write sales equals advertising plus bonus plus, okay? So, and region, okay, this one, okay? This one, you're gonna write this way, sales B naught, B1 times advertising, B2 times bonus, okay? Plus B3 times what? X1, B4 times X2, X4, X2, sorry, X2 plus C. X1 and X2 represent as an indicator variable. Here, Midwest 0. Let's say this one is West 1 and South is 0. Midwest 0, Midwest 0, West 0, South 1. You have to, after that, applying this formula, you have to make sure that that you're gonna get the answer through that way. See? This is same thing as I'm gonna take out this one and say, hey, sales B naught, B1 add plus B2 bonus plus B3, I would say West plus B4 South. That's the same thing. That's the same. That's the same thing. Then you can particularly see that each region gonna have that how much sales. If you want West, what are you supposed to do? Sales, in order to check the sales, you put the 1 here You know, you're supposed to put 1, okay? This x1 means west, x2 means south now, okay? Put 1 here, 0 here, and the rest would be same as just we have the value. And then you're going to reduce that equation to the one that we know. If you want to check that sales in that south, put 1 here, 0 here, and you get the equation for that one to predict that sales in that particular region. If you want to find the sales in Midwest, put 0, 0 for both of them. See, 0 and 0 for both of them. It's implied, okay, already because this B1, B naught is not only for this guy, B naught is for this guy too. So you don't have to get the B naught and say these are for that particular region. No, no, no. You don't have to say like that. But it's implied. You know that if you need the south, Midwest, Midwest is the base. Midwest is the base. Okay. So that's what they were trying to do over here. See, they set this up and see, set up like this way. In order to do that one on our that on the code, I'm gonna change it. See, rather than using this one, you didn't find anything. See, region, Midwest 0, region, South 0, region, West 0. My region South is 1, West also 1, but the region 0, Midwest is a 0, that's the base. So this is the base. Okay. So let's run this one. And then let's run the regression. Okay. For whom? Advertising, bonus, south and west. B0, B1, B2, B3, B4. That all the values are over here. That's the one they have set up over here. See, plugging into here, 435. Plug in here. See? 435, 1, 970, 258, 210. See? Plug in over here. And then later on, if you want for the certain region, now you can do the way that we were talking about earlier. If you want south, south is 1, west is 0. Boom. Simplify, you get this equation. And if you want west, west 1, here 0, the rest stays the same, and simplify. And midwest 0, 0, you're going to left over with 435, 137, 1.37 plus this. Now you have a 3 equation for 3 regions. That's how we're going to do it. Then later on, we can talk about there some kind of that interaction term can be added, and that's how we're going to do it here. See? Okay. Southwest, or that if you want advertising and bonus, like that, you see. If you want the average sales, then Southwest regression, I don't know why we. Oh, these are the interaction terms later on. Okay, later on interaction terms. Regression. Yeah, this is scatter plot. So like, just we're gonna continue this discussion. I want a little bit just like a 5-10 minutes, like a maybe 5 minutes. We want to look at the homework 3, and then we continue the discussion. Let's see, we're gonna do this kind of thing. At a certain point for the language, you have to do that thing. See? You're gonna write that one. See? Reg, if you want to go with the language reg. And later on, I have to talk about that some selection procedures too to get the best model. Okay, I like to talk about that one too, which is we're going to talk about later on. But since this homework is due by this coming Sunday, we were supposed to cover that to chapter 8, in which that we're going to talk about the selection procedures. See, here they were given everything with that's the data, some data of the sweep data, and they were wages, log wages, education, and age. The scatter plot. The scatter plot. pages of pages, something like that. So in addition to that one now, so it's been grouped by C scatter plot, wages and education, wages and education by the gender, and their regression line by gender. So it's gonna happen. Same thing that we saw earlier for the sales versus salary versus education. Okay, same pretty much same way. You see, they were so parallel look like. You see, scatter plot for the males and females. So wages was education by sex and by language, same thing. You can get this done by languages. There are three languages we were talking about: English, French, and other three lines. That plots and their regression line. So on this side, we have an education level has been done with the categorical variable. See? Now we do the education and age only, which are that only that quantitative variable, no categorical variable. This setup has been drawn with respect to the language, with respect to the gender. That's a different story. So it's a regular regression. This is a multiple regression. It's a two variable. For the regular properties, you can talk about that on B0, B1, B2. Okay, those are standard. And then the age variable as a regressive variable, education and age, log wages. Instead of wages, they were talking about the log wages. Okay, if you do that one, how it works. So the y has been transformed into that log values. Sometimes transformation, see, residual, see, more like that one. We can check those things. Okay. And now see, I'm gonna add the language to gender to language to. I change everything. I'm gonna say sex to, then now I call the gender. Male, I'm gonna convert to 0 and 1 for the numerical. See, so then they can be taken as a like a number equation. I'm gonna keep gender as a gender. Okay. This one converted into 0 and 2 numbers. The earlier that when we were talking about here that 0 and 1, we put the other way around, just the region as a region, see. But we coded them. Can you remember that when we were talking about that in chapter 7? We coded with the numbers, okay? Without numbers, you cannot run the regression. Keep in mind, categorical variable, you have to have a numbers, okay? You have to have a numbers. Region 1, 2, 3, you call that one 1, 1, 1, 0. Oh, here, see, numbers. You need the numbers. You had the numbers. Only thing I changed to that the just the levels. Okay, that's a different thing will be there. But keep in mind, these numbers should be there. But in our homework, we don't have numbers. You have to set up the numbers. That's what we are doing over here. See? When you don't have a number, sorry, not this one that we were talking here. See, they gave the male and female. I cannot do anything regression. You cannot run regression with these ones. You have to have a numbers. Some see dummy variables to be included with the numbers. See? Numbers. See? Look at what I do. Then you run regression. Okay. Same thing. Make sure. Okay. Make sure that what we're doing is clear to you. See, I'm going to talk about that one again and again. But you, if they have given levels like a non-smoking, former smoking, blah blah like that, you have to make sure you put a dummy variable and then run the regression. Because otherwise, without a dummy variable, you cannot get the answers. Okay. Look at the because you need the numbers. See, these are dummy variable. Gender is a dummy variable which has a two options, 0 and 1. Language reg is a dummy variable which has a three options, 0, 1, 2. Doesn't matter. If you want, you can just define any way you want, or you can just simply say that with this one we can, these three can be represented by another two, x1 and x2. That's another way, x1 and x2, or just same thing being converted into numbers. See, look at different ways we can get this done. Can you remember when we have a three levels? Those three levels can be represented by x1 and x2. Let's say this one, you have taken x1 for this guy, and x2 and x3 should be utilized in order to represent French, English, and others the way that we did earlier. Or you can do this way. Simply, you're going to say English is 0, French is 1, others numbers. You can tackle that way too. And then get the answer and then filter the discussion. Instead of wages, you put the log wages. Like that. So up to there, I think that the rest of I can talk about that Wednesday while we going through the homework and this stuff. That's the plan. Okay. So remember what we did over here. These changes do here. See, I changed this one name of the variable as well as the this number new categorical this string has been converted into a number 2 for me to run regression. But in the 7 here, they had the numbers. They had the numbers. What I did was, instead of using male 0, 1, I wrote with the aid of their levels. See, that's a different thing. Kind of like the same thing, but numbers are already there. But we don't know which number gonna go which one. If you go call this one gender, how do you know which one to go which one? We call for the women put the 0, for the men give the 1. I change the names too. See? Yeah, like that. Several things we did. Look at what we did. Males convert into gender, and then I put into female, other way around. What I this it is a backward, okay? Here I have that one, female and male. Okay, sorry. Female and male names I converted to number. Here I have the numbers, I convert into what? Male and female. See, depends on the situation. This go the forward process. Here we go to backward process. So what I'm gonna do, see, because we have enough time, we can easily cover because there's no any heavy theory behind that one. Next time we can cover even the variable selection process, because this one in chapter 7, this is the major part that we have to talk about, that how to tackle with that indicator variable, plus little bit I'm going to talk about the interaction term, how they interact with and how it's going to affect to the our the calculations at the end of the day. Interaction terms comes into the picture, and under the variable selection procedures, we talk about the multicollinearity and then how to pick the best model. Okay, best model. That part is coming because when I'm gonna ask that what is the best model, you have to make sure you run everything and give me the best model at the end of the day. You need to look into so many things. We're gonna come to that one. Adjusted R squared, something called the CP. CP means Mallows. Mallows statistics, root mean squared error, R squared, adjusted R squared, CP, this one, in addition to these three methods, forward, backward, and stepwise. Out of all these methods, you should come up with the best method, best model at the end of the day. Okay. So those things we're going to talk. These are very interesting part. This is the one that really utilizing data mining. And the extension of this one is called the principal component analysis, discriminant analysis, classification, cluster, those kind of stuff. Let's see how much that we can cover that. If time permits, we can go to the cluster analysis too. Principal component analysis, we're definitely going to cover. And if time permits, I can go to even the time series, but I don't know. Let's see how it's going to work. Okay. So I'm planning to stop over here. Do you guys have any question? Anything that you want to discuss? I'm grading right now, okay? I'm gonna return all the homework and assignments and everything, okay? If you don't have any questions, okay? I'm planning to stop over here. And then you guys have a good night. And then let's see you guys on Wednesday, okay? So thank you very much. And then have a good night. Stay safe and be well. And then see you guys on Wednesday. If you have any question or any need, then just email me too, okay? Thank you very much. Have a good night. Take care. Thank you very much, okay? Thank you. Thank you very much. Thank you very much.